This is the very last unit of the course, Unit 4, Topic H. We're going to be looking at the applications of the definite integral, and this is really just a very, very small sampling of the applications. Working more with integration and all of its many applications is a topic that we start with in Calc 2. So I would encourage you to go on and take another calculus course if you'd like to know more about what we do with integration. All right, our first application is just what we've already talked about, but I'll remind you of it. One thing we use integrals for is to find the area under a curve. So if I wanted to find the area bounded by the graphs of y equals e to the x plus 1, y equals 0, x equals 0, and x equals 2, I could make myself a quick little sketch here. E to the x plus 1, that's just your standard exponential growth function shifted up 1. So y-intercept will be 2. And it'll basically look like that, right? Use a calculator if you want to, but we all know what exponential functions look like. Y equals 0, that's our x-axis, that's a boundary. And then from x equals 0 to x equals 2. So I would be looking at this area, and that's what I want to try and figure out. Again, nothing really new here. We developed the integral as the area under the curve, so you're very familiar with this. We'd simply take the integral from 0 to 2 of the function e to the x plus 1 dx. E to the x plus 1 provides the height. The dx would be the base, and that base times height gives us our area. The antiderivative of e to the x is still e to the x, plus the antiderivative of 1 is x, from 0 to 2. Plugging in the top value first, I'd have e squared plus 2, subtract, and now I have to plug in the 0, e to the 0 plus 0. So that's e squared plus 2 minus e to the 0 is 1. An exact answer for this would be e squared plus 1. Of course, we could also get a decimal approximation. About 8.39. So, just one example of that because you've seen it quite a bit before. Our next example talks about finding the net change of a quantity. If I want to find the net change of some quantity, capital F, on the interval from a to b, then what I'll do is I'll integrate the derivative of f from a to b, which of course turns out to be f of b minus f of a. Just a FTC there. All right, in our example, we have the following object's velocity in meters per second is v equals negative 9.8 t plus 5. I'd like to know how far does it fall between the first and third sections of motion. If we keep in mind that v is really the derivative of s, what I've just been told is the derivative of the position function. And if I want to know how far it falls, I'd like to know what is the net change in position. So what I'll do is take the derivative of position, also known as velocity, and I'll integrate that derivative from 1 to 3. So the distance that the object falls, integral from 1 to 3 of that derivative function, negative 9.8 t plus 5 dt. Antiderivative here would be negative 9.8 times t squared over 2 plus 5t, evaluated between 1 and 3. This would be negative 4.9t squared plus 5t, evaluated between 1 and 3. So negative 4.9, and I plug in the top value first, times 3 squared, plus 5 times 3. Subtract negative 4.9 times 1 squared, plus 5 times 1. And then that's just a great big calculator problem to plug in. The first set of parentheses, when I plugged that in, I got negative 29.1 minus, plugging that one in, I got 0.1. So it looks like we're going to get negative 29.2. And that's a distance, so that would just be in meters. It's only negative because it's falling. So since it really asks me how far does it fall, probably a more reasonable answer would just be the 29.2. I really don't need to include the negative if I say the word falls. So it falls 29.2 meters. All right. Another application of integration is to find the average value of a quantity. The average value of some function f on the interval from a to b is 1 over b minus a times the integral of f from a to b. So, if I go back to my same problem here, my falling object, I was given the velocity function. If I want the average velocity between the first and third seconds of motion, I'm going to say a is 1 and b is 3. So the average velocity is, according to this formula, 1 over 3 minus 1 times the integral from 1 to 3 of the velocity function. Right? Now this is the integral we just did, right? We just calculated the value of that integral, and we got negative 29.2. So I have 1/2 times that negative 29.2, which would be negative 14.6 meters per second. So the average speed or velocity if we include the negative, would be 14.6 meters per second over the course of those 2 seconds. All right, we've been talking about these motion problems, and my last couple of examples here, well actually, yeah, last couple of examples I guess, are just there to remind you about the relationships between position, velocity, and acceleration. If s is our position function, in our case we often think of it as the height of a falling object, then s prime will give me the velocity, and the second derivative, s double prime, will give me the acceleration. Using integration, we can actually go backwards. Instead of starting with position and taking derivatives to get velocity and acceleration, we could start with acceleration and integrate to get velocity, integrate again to get position. So we're literally going through the process backward. So if a is acceleration, then the integral of a dt will give me velocity, and the integral of the velocity dt will give me the position. One way to kind of summarize these things with a diagram that I often use is if I have my position, my velocity, and my acceleration. To go down this list, I have to take derivatives. To go up, I have to take integrals. And that little diagram just sometimes helps me remember how to go from one to the other. All right, our example. Given the velocity function, v equals 3t plus 2, and the fact that the object's starting position is s equal 5, find position, velocity, and acceleration at time 7 seconds. So we were given the velocity function. We were given the one right in the middle, right? If I take a derivative, I'll get acceleration. If I take an integral, I'll get position. So let's see here. Let's start with the position. The position s is the integral of the velocity. So the integral of 3t plus 2 dt, that will be 3 times t squared over 2 plus 2t plus a constant of integration. Or if I want to, I could write that as 1.5 t squared plus 2t plus c. That's my position function. Now they gave me enough information to solve for that starting position, right? We do know that the starting position is s equals 5. So I'm going to go ahead and say that at the beginning, at time 0, s has to be 5. And plugging that in, I can see that c is 5. So my final position equation, s of t, is 1.5 t squared plus 2t plus 5. Let's do acceleration, and then we'll substitute the 7 into everything at once. Acceleration is the derivative of velocity. So if I take the derivative with respect to time of my velocity function, 3t plus 2, I'm just going to get 3. So the acceleration function, technically a of t, is actually the constant function, 3. All right, the last part of this asked us to evaluate position, velocity, and acceleration, all at time 7 seconds. So at t equals 7, let's see, the position, s of 7, I'll just plug 7 into there. Now let's see, what do we get? Uh, 92.5. And I think they told us that, did they? Yeah, they actually didn't. I guess they didn't give us any information about units. Let's just assume we're talking about distance units of meters here, since I didn't tell you. So after 7 seconds, the position would be 92.5 meters from wherever we started, right? Or actually, excuse me, from some arbitrary starting point, which we called 0. Velocity. V of 7. V is the one they gave us, so 3 times 7 plus 2 would be 23. And since I've chosen meters here, that would be in meters per second. So at 7 seconds, this object is moving in the positive direction at the rate of 23 meters per second. And then finally, acceleration, a of 7. Our acceleration, the time actually doesn't matter. It's always 3. And that would be in meters per second squared. All right, so keep in mind, anytime you're given any one of those three, position, velocity, or acceleration, you can always use these relationships to find the other two. That brings us to the end of the section and the unit and the course.